The Future of Humanity Institute has shut down. I hope this isn't an omen. Let's have a look at what happened. The Future of Humanity Institute was one of the few places worldwide studying the risk of human extinction and, well, some other things. It was located at the University of Oxford in the UK until its demise earlier this year, which was announced last week. The institute was founded in 2005 by Nick Bostrom. That's the guy who believes, among other things, that we live in a computer simulation. More about him in a moment. The maybe most impactful work to come out of the Institute was to get artificial intelligence on everyone's agenda as a potentially existential threat to the entire human species. About 10 years ago, the Future of Humanity Institute became strongly linked to the effective altruism movement by the work of several philosophers, including Hilary Greaves and William MacAskill, who are also in Oxford. Effective altruism is a research area and community of practice which tries to use economic reasoning to find the most effective way of improving the world. This sounds all well and good, but this line of thought later gave rise to the more controversial idea of long-termism that was strongly represented at the Future of Humanity Institute. Long-termism says that altruism should focus on benefiting the long-term development of humanity because, if all goes well, many more humans will live in the future than now. In this illustration, each grain of sand illustrates 10 million people. The green grains are those alive today, that's about 8 billion. The red ones are those who have lived in the past, about 110 billion. But that's just a tiny part of all the lives that are yet to come, unless we go extinct. And so long-termists argue it's only rational to focus on all the many people who will be born in the far future. Those currently alive only matter insofar as they need to produce sufficient offspring to avoid extinction, but with 8 billion people on the planet, we could spare a few billion. In a 2019 paper, MacAskill wrote, "For the purposes of evaluating actions, we can in the first instance often simply ignore all the effects contained in the first 100 or even 1,000 years, focusing primarily on the further future effects. Long-termism basically gives rich guys an excuse to pursue their future visions while ignoring the suffering of people around them. Not so surprisingly, Elon Musk has found long-termism very compatible with his way of thinking. Others have decried it as anti-democratic and anti-humanistic, and many of the effective altruism crowd have distanced themselves from it." The questionable moral value of long-termism probably didn't make the Future of Humanity people popular with their hosting institution, but the major problem seems to have been that the institute ran into administrative problems. In their final report, you can read that they were affected by a gradual suffocation by faculty bureaucracy. The flexible, fast-moving approach of the institute did not function well with the rigid rules and slow decision-making of the surrounding organization. They also write that several times we made serious missteps in our communications with other parts of the university because we misunderstood how the message would be received. According to Anders Sandberg, who worked at the Institute, one of the issues was that as university employees, Institute members were not allowed to nap in their offices. Then, starting in 2020, the faculty imposed a freeze on fundraising and hiring, and this would basically have spelled the death of the Institute. But I have a hard time seeing how this was just about admin issues, because it means that the faculty decided they're not getting much in return for their trouble. Well, maybe in 2020, the Future of Humanity people were still hoping to put up camp at a different department. However, last year, Nick Bostrom drew unwanted attention to himself because of text he'd sent 26 years earlier over an email list. In this text, he lays out his opinion that black people are intellectually inferior. After that text surfaced, he wrote an apology, which he, however, mainly used to elaborate on how his views things are so much more intelligent now than they were then. If the Institute still had any hopes to muddle through at that point, this episode would have killed those hopes. Bostrom's pseudo-apology has the same spirit that you can also sense in their final report. It basically says, we are so advanced that those intellectually inferior normal people just can't comprehend our greatness. The Future of Humanity Institute should not be confused with the Future of Life Institute. That's the brainchild of Max Tegmark and the place which published an open letter last year asking for a pause on AI development. That pause has of course not happened. Instead, everyone keeps on screaming and yelling how AI is going to kill us all, and it'd be funny if it wasn't so stupid. But maybe one lesson to take away here is that even if humanity doesn't have a future, life will continue. Astrophysicists say that 95% of the matter-energy content of the universe is dark stuff, either dark matter or dark energy. It's supposedly all around us, but we can't see, feel, or hear it.
Yes, you can.
Shut up! I'm not particularly excited about most of the experiments looking for this dark stuff, but a few days ago I read about a new one that actually makes a lot of sense. Let's have a look. So this new proposal comes from a team of NASA researchers, and they're suggesting to use 4 small spacecraft that fly around in the solar system in the configuration of a tetrahedron. The idea is fairly simple. They want to very precisely measure the distances between the spacecraft to look for deviations from Einstein's theory of gravity right here around us. This makes a lot of sense because, you see, we know from observations that this dark stuff makes itself noticeable on large distances. Galaxies, galaxy clusters, the expansion of the entire universe. Whether it's really some sort of stuff or whether we have got something wrong with the law of gravity, the differences kick in only at large distances, and for some reason we can't detect it on our planet. But somehow these two things have to fit together, so nature must interpolate between this local Einsteinian gravity and whatever's going on out there in the cosmos. This means that there should be an effect in the solar system. It's just that it's so small that it's hard to measure. This is why precision tests of gravity in the solar system make a lot of sense. If you look at the explanations that have been proposed for dark energy or dark matter, like modified gravity, they all need some sort of interpolation between galactic and Earth scales. They have a mechanism that makes those effects go away close by the Sun, but they never entirely shut down. Modified Newtonian dynamics is somewhat awkward in that it doesn't tell you exactly how the modification shuts down. It just has an arbitrary interpolation function. But there are other ideas, for example, chameleon fields that could make up dark energy. They have what's called a shielding mechanism that suppresses these fields near heavy objects like our planet or the Sun. But they don't go away, so you can measure them if you measure precisely enough. But how? Let's then talk a little more about this new proposal. Why do you need 4 spacecraft? It's because if you have only 3, there's always a plane that goes through them. If you have 4, that's a really 3-dimensional configuration. What you do then is that you precisely track the distances between the spacecraft by pinging back and forth the laser signals. This also allows you to measure the relative velocities. And from the changes in the distances and velocities between the spacecraft and their relation to the distance to heavy objects, mostly the Sun, you can then infer whether the law of gravity is as Einstein said or has subtle deviations. Albert thinks that's a really cute idea. This type of experiment will not detect dark matter, at least not in the most common versions, but it could pick up some type of superfluid dark matter, which I've worked on for some time. This isn't mentioned in the paper, but the superfluid dark matter also has a kind of screening mechanism, which is that the superfluidity must go away near heavy objects. The idea is that this happens because the gravitational pressure gets too large. So in this model too, you must have a crossover somewhere. This is why I think this experiment is a really good idea, because it looks for a generic effect. Does gravity in our solar system depend on the distance to the sun as we expect? We know that there can't be any large deviations, because otherwise the orbits of planets would be weird, but this experiment can look for subtle, small deviations. I think this is more promising than pretty much all of the dark matter experiments that are popping up left and right these days. I could talk about a new dark matter experiment every day if I wanted to. Like, physicists are using everything as dark matter detectors now. DNA, rocks, quantum computers. I'm about to write a paper claiming that my phone is a dark matter detector. You see, if a gravitino comes by, the phone will ring. That's a negative result, which will make for a very interesting new bound on gravitino phone calls. I'll submit this straight away to Nature. I got a couple of questions last week about a supposed world-first breakthrough converting carbon dioxide into electricity that was aired on TV in Australia. They say that a lab in Queensland has developed technology that's, quote, not just carbon neutral, but one step better, consuming CO2 and creating power. Or, with the proper Australian accent,
generating a current that's not just carbon neutral, but one step better, consuming CO2 and creating power.
So we'll just make energy out of air, problem solved. It sounds too good to be true, doesn't it? I looked at the paper and it's true. But it doesn't mean what the TV people suggest it means. Let's have a look. The paper that the TV clip is based on was recently published in Nature Communications. It comes out of the Department of Chemical Engineering, but of course chemistry and engineering are really just physics, so I feel totally competent to comment on this. The only relevant thing you need to know to understand this news is that you can extract energy from any system that's not in equilibrium. That it's not in equilibrium doesn't mean it recently had a nervous breakdown. It means it hasn't yet reached maximum entropy. It's still ordered in some sense. Say you put ice cubes into a glass of hot water. This system is not in equilibrium because it's ordered. It has low entropy. On top it's cold and at the bottom it's hot. And guess what will happen next? The ice will melt, cool the water, and the entire system will reach equilibrium at a common temperature. This is when the entropy has become maximal. As long as a system isn't in equilibrium, you can extract energy from it. For the water glass, you could, for example, use a thermoelectric generator. That's layers of materials which convert a temperature difference into a flow of charged particles, so that's electricity. For the same reason, you can generate energy from the so-called waste heat of, say, data centers or subways or cremation centers. It's because the excess heat creates a temperature difference with the environment and you can extract energy from that. Yes, some cremation centers actually do generate energy from burning corpses. It's like burning the midnight oil, except it's your great aunt Mildred. But you can't just extract energy from temperature gradients. You can also do this, for example, for a difference in the salinity of water. If you have two bodies of water with different salinity that meet, you can extract energy from that. This was also recently in the headlines. I didn't talk about it because, well, besides this sentence, there really wasn't much to say. Again, that works because this system isn't in equilibrium. The salinity wants to equalize. You can then use diffusion in a suitable medium to generate a flow of ions from the salinity gradient, and again, that gives you an electric current. You can do the same thing with, say, different levels of moisture in the air. These technologies usually generate very small amounts of power, but yes, you can extract energy from the air. It's not magic, it's physics. This new work now is somewhat puzzling at first sight in that they seem to not be using any sort of deviation from equilibrium. The TV clip just says they convert air to power. But if you look at the details, that's not how it works. In the paper, they explain that they use some kind of porous material that absorbs carbon dioxide. The absorption of the carbon dioxide causes ions to move, and that generates a current, so we get electric power out of it. But the material can only absorb the carbon dioxide because it isn't saturated already. It's not in equilibrium with the surrounding air, and that's why you can generate energy with it. But this process will eventually stop when the material is saturated. They didn't say this in the TV clip, but it's clearly stated in the paper, where they discuss how they can get the carbon dioxide back out of the material and what you could possibly do with it. Reversing the material to its initial state will require energy, and since chemistry doesn't have zero-sum games, it'll take up more energy than the process generates. So I'm afraid it's not going to create energy out of nothing. That said, I don't want to belittle this sort of research. It's very interesting. There are a lot of devices that can be powered by small energy currents that can be extracted from the environment. And these low-energy devices are bound to become vastly more numerous with the Internet of Things on the way. The idea might even come in useful to make carbon removal more energy efficient in the future. So it's not magic, but if you know the details, it also doesn't sound quite as big a breakthrough as they put it on TV. I was skeptical about electric vehicles until I learned that battery-powered cars accelerate faster. Since then, I've been convinced that electric vehicles are the future, obviously. But recently, I've changed my mind. I now think that hybrids are the future, obviously. This opinion shift was caused by a number of things. For one, the transition to electric vehicles will require a substantial extension of power grids globally. And of course, it's not done with the grid alone. Also, the energy has to come from somewhere. The estimated costs for this are staggering, and it's rather unclear how this will happen by the time that we're supposed to all be driving electric vehicles. In the European Union, for example, all new car sales are supposed to be electric by 2035. This isn't new. I went through the numbers in a long episode a year ago. What's new is that it's becoming increasingly clear that the transition isn't going as smoothly as hoped because many nations are simply not doing what's necessary. The International Energy Agency, IEA for short, warned very clearly in a recent report that the electric grid extension is the weak link in the energy transition. They say that to meet climate goals, the electric grid needs to be expanded at least 20% faster over the next decade than it did in the previous decade. The problem isn't just electric vehicles. The issue is also that renewable energy power plants need to be hooked up to the grid. According to the IEA, there are more than 3,000 gigawatts of renewable energy projects awaiting connections to the grid, with half of those projects in advanced stages. That's right, they're building renewable energy power plants, but we can't use them because they're not connected to the grid. According to estimates from the non-profit organization American Action Forum, by 2035, the costs for the grid upgrade could reach as much as $500 billion, though others have put the cost somewhat higher. In Europe, the numbers are similar. The European Commission estimates the necessary investments into the grid are 584 billion euros until 2030. Where's that money supposed to come from? Well, the European Commission says it'll come mostly from private sources, which sounds like a very well thought through plan indeed. What's the problem? According to McKinsey in the United States, the construction of new charging places for electric vehicles has picked up in the past years. But still, companies face obstacles because of missing personnel and partly because of missing hardware, such as specific types of transformers. It's basically a coordination problem. You can't just ramp up one sector of the economy on the snap of a finger. You'll need to also ramp up all sectors that supply it. In the EU, a big part of the problem is, guess what? Bureaucracy. For example, in Spain, the company Repsol built 1,600 charging stations in the past 2 years, but more than half still lack a power connection. That's because the company must get a license for the grid connection, and the responsible office is just extremely slow with doing the authorization process. A similar problem exists in Germany, Europe's biggest economy, where it can take months until a completed charging station is authorized and hooked up to the grid. In Germany in particular, the outlook for electric vehicle sales is bleak at the moment. It's because at the end of 2023, the government discontinued subsidies for electric vehicles, which has led to a major sales drop. And that isn't going to make companies more enthusiastic to build charging stations, and that in return won't encourage people to buy electric vehicles. By the way, if you remember, I had to buy a new car and was wondering if I should buy an electric one. I ended up buying a gasoline-powered one. Yes, I'm terrible. The major reason is that the town where we live has a total of one charging place and we don't own a house. And then I heard an advert for a Nissan car with the slogan "Tank fuel, drive electric." And I thought, genius! You see, Nissan now offers a car, the Qashqai e-Power, that drives fully electrically, but the battery is charged by, wait for it, a combustion engine. It's not terribly energy efficient, and the car got some bad reviews because it actually eats up more fuel per mile than some cars that are powered just by combustion engines. But will it matter if people really buy electric because they like the acceleration? Finally, I think what tipped me over to hybrids is that all this talk about what to do with vehicles has made me realize just how good hydrocarbons are as energy carriers. Hydrogen, methane, ammonia is all really nasty stuff to deal with. But gasoline, wow, it smells good. So at the moment, my prediction is that this transition to electric will gradually be weakened in the next 5 years or so, as it becomes apparent that the grid extension isn't going anywhere near quickly enough, that renewables aren't coming by anywhere near fast enough, and that batteries aren't improving as quickly as they say. We'll still go mostly electric eventually, I think, because it's the most efficient option, but it'll take much longer than the plans say. You should bookmark this video so that in 5 years you can laugh about how wrong I was. A recent investigation has revealed that the final steps of phasing out nuclear power in Germany were partly based on false information. And it doesn't look like it was a mistake, but a deliberate rewriting of what was originally accurate information. The ministry denies everything. Let's have a look. The news broke a few days ago after the German magazine Cicero demanded a release of communications from the Ministry for Nuclear Power and Safety for the time during which they were preparing information for the parliament in 2022. The Germans have always been weird about nuclear power, with a very strong anti-nuclear lobby that was represented in particular in the Green Party, which ended up in the parliament in the late 1990s. The Fukushima accident in 2011 increased public pressure to phase out nuclear power. The decision to go through with it was passed with a broad majority in the parliament across all large parties. The last nuclear power plants were supposed to go off the grid by the end of 2022. But come February 2022 and Russia invades Ukraine, suddenly gas supply is at risk. At that point, a lot of people asked quite reasonably if not it might be a good idea to keep the remaining 3 nuclear power plants running for as long as possible. This might sound easier than it is, because the phase-out had been scheduled for such a long time, safety checks hadn't been updated. Those could have been done on short notice, but a bigger problem was that the owners hadn't ordered new fuel rods, and the delivery time for those is a year or so at least. That said, fuel rods don't burn out suddenly from one day to the next. They just become gradually less efficient. This means you can keep nuclear power plants running on fuel rods that are past their best years. It's just that they'll produce less and less power. Also, I was told by people who I thought knew what they're talking about. But the parliament decided to go through with the phase-out, quoting safety concerns, though industry pressure then had them postpone the shutdown until spring 2023. No word about ordering new fuel rods to get the power plants back online later in the year. Well, the new report explains what happened there. It reveals that the expert committee that was tasked with advising the ministry actually wrote that it would have been possible to continue running the nuclear plants that were still online for several years, and that this would have been compatible with nuclear safety requirements provided certain steps would be taken and new fuel rods were ordered. This is what I had also heard and read. But someone in the ministry, who was not a member of the expert committee, then rewrote this passage so that the final version said that postponing the shutdown of the 3 still running nuclear power plants beyond the scheduled date of December 31st, 2022 is not compatible with safety requirements. Of course, the ministry is now denying that anything weird ever happened. Well, I think this is pretty damning evidence that something wasn't going right, but it's questionable that it made much of a difference, because in all fairness, at that point it was already too late for nuclear power in Germany anyway. They should have invested into new nuclear power plants 10 years earlier rather than taking the existing ones off the grid. The most interesting part is maybe how many people in Germany are upset about this. It really shows how much the public attitude to nuclear power has changed. It used to be that environmental organizations argued that phasing out nuclear power was to force the expansion of solar and wind. But of course, if they had wanted clean energy, they should have phased out coal, not nuclear. Though, to be fair, it worked to some extent if you look at the electricity sources in Germany today. In case this looks impressive, this graph shows the installed capacity, not the electricity that we actually get. A lot of installed capacity for solar doesn't deliver. If you look at the electricity we actually get to use, it's not quite as impressive. Next thing to keep in mind is that a lot of the energy we use doesn't come from electricity at all. For example, we pretty much all heat with oil and gas here. If you look at the total energy mix, that doesn't look quite as good anymore. And now this big chunk of fossil fuels is supposed to go and be replaced by what, I wonder? I certainly hope that the German parliament won't fall for the psychological trap in which they can't reverse a course of action because that'd mean admitting it wasn't a good course in the first place. That's what I hope, but what I expect is that they fall into exactly this trap. So keep on dusting the solar panels, guys. Thanks for watching. See you tomorrow.